Welcome to our CIS545 final project on taxi trips in New York City. So to give you a small overview, first we're going to talk a little bit about our objectives and our data set. Then we'll move into what we did in EDA. Third, we'll move into our modeling and the insights we gained from there. And then we'll take you through a conclusion where we talk about challenges and limitations, as well as some potential future work with the data. So what we're trying to do here is try to get a little bit more fair transparency for New York City taxis. With the rise of Uber and Lyft, there's been a lot of fair transparency with those apps for New Yorkers, and it makes it a lot easier for New Yorkers, and it makes Uber and Lyft much more attractive options for transportation than yellow taxi cabs. The traditional yellow taxi cabs do not have fair transparency. People don't know what they're going to pay when they get into the cab. They only know after the ride. So what we're trying to do here is trying to see which factors affect fares and what causes which factors have what effect on fares, as well as to see if we can maybe make some predictions about, given certain factors, what would your fare look like. Next, please. So to do this, we combined three different data sets. The first was a trips data set that had 100,000 instances of trips in it with a bunch of different data, such as time, date, pickup and drop-off location, number of passengers, many different factors. And we're going to use this as our main data set. We merged two different data sets into that. The first was the zones data set that comes from official New York City taxi data, which tells where each of the zones actually physically are located in New York. And we also added in baseball data to give some event data to see if whether the Yankees or Mets playing at home had any effect on cab fares. Next, please. So we first went through data cleaning with 4 steps. The first was we found that most of the data was in the summer, so we removed the non-summer rows. Then we dropped rows that had negative fare values, as well as columns that were either redundant or not going to be relevant towards predicting fare. Third was we took the zones and we extracted their latitudes and longitudes to create new latitude and longitude variables. And fourth and final was we took our trip time string, converted to Unix time, and also added in indicators for morning, afternoon, evening, or night, depending on when the trip was. Next, please. Then for EDA, the first thing we did was a correlation matrix, and we discovered that the correlation between fare and trip distance was very high, which makes sense, but it also kind of affirmed what we were thinking. Next slide, please. And then also we analyzed drop-offs and pickups to see which places had the highest amounts of drop-offs and pickups. We found that East Harlem South and East Harlem North had the highest amounts of both drop-offs and pickups, but that with regards to pickups, there's a lot wider gap between these two highest locations as opposed to the other as opposed to drop-offs where it was a little bit more condensed.
So we also wanted to take a look at the fare and see the spread between how the fares range. So we see from our graph here, which is actually interactive in our notebook using Plotly, that most of our trips are under $20 and even mostly under $10, which we thought was surprising because New York is quite expensive, but we realized, oh, maybe it's because a lot of the trips are in Harlem, which is not necessarily a touristy area. Then we wanted to see the trip duration for these inexpensive trips under $10. So we noticed that they were mostly under 20 minutes, which makes sense because a shorter trip would have a lesser fare.
So one of the main problems we wanted to solve with respect to our modeling was that the taxi zones, as they were given to us, were nominal data, meaning that zone 1, ID 1, and zone 2 had no greater relationship than zone 1 and zone 100. And so we decided that we had 2 approaches for handling this and making the data of pickup and drop-off zone more interpretable. The first I'll discuss, and the second one will come later. So the first one was converting the zones into latitude and longitude, creating continuous features that allowed us to model on them. So we started with a simple linear model, which provided our baseline, and we see that the mean squared error, which was our chosen loss function, we also put mean absolute error as a baseline, just for reference. But for mean squared error, our initial was 39.2. And that showed us what we were kind of trying to beat. Then we moved on to some regularization, but found that it made no improvement. In fact, actually, it was a little bit worse when we created ridge and lasso models. And so we decided to see what decision trees would look like. But this actually created the worst results so far, going all the way up to 61. And so we realized that going towards ensemble would probably be our best bet, especially to reduce some of the variance. And so we started with a random forest model, which you can see is the first and very significant improvement that we had, going all the way down to around 30. And so from there, we wanted to tune some of the hyperparameters. Next slide. So you can see we varied the number of trees in the forest, and we found that 150 trees gave us the best loss. And this brought us down to 29.96, so a little improvement over the standard forest. And from there, we decided to consider whether boosting would give us an advantage. And we found that our initial boosting model brought us a few points down to around 27. And so since that was our best one so far, we decided to do a more intense hyperparameter tuning using grid search CV, and found that we were able to get mean squared error all the way down to 25.57, a significant improvement from our original around 40. And that taught us some interesting things. So thank you. Next slide. So the second approach we decided on the pickup drop-off zone was turning them all into binary features, meaning a 0 and 1 if this trip was picked up in the particular location, or 0 and 1 in another column if it was picked up in another location, etc. So we decided to skip linear models because we thought that decision trees works better on binary variables. And so we found that already we're strong at around 33.9, which is, if you remember, is better than the tree model for the latitude longitude version. And so we moved to ensemble again, creating a parallel between the different approaches to compare them. So our random forest brought us down all the way down to 21.9, a massive improvement from our baseline, if you remember, which is around 40 in the few slides back. And then again, we continued to gradient boosting and then started tuning some hyperparameters and found that the best thing we could get was 19.8. So now, thank you. So now we can see the comparison between the different approaches. And you can see again that the binary approach was much more fruitful, but moving to ensemble was better in every event. And you can see the great improvement we had from our baseline model all the way down to our final model. Next slide. So we wanted to consider what were the important features. So the truth is trip distance and trip duration naturally were significantly more important than any other feature, but we still also wanted to check to see if there were any zones that were significant. And it was interesting to note that there were some zones that had a larger impact on the model than others. Interestingly enough, South Ozone Park, whether you're getting in or getting off there, had the most impact with respect to the different zones. Which suggests that the great geographic location actually does have an effect as we expected. Next slide.
So now to get into some other insights from our latitude and longitude models, we know that these have a greater spatial relationship, but they actually ended up falling short when we consider them linearly. For the binary zone models, when we combined it with gradient boosting, we ended up getting balance between capturing the essential geographic features and avoided overfitting. So it actually ended up being more effective for the binary zone models, which is interesting because it seems that for some data sets or features, a simplified representation like this binary zone model, as opposed to the latitude longitude, actually might be capturing better results for us. So some challenges with our data is that there's high dimensionality, which can be mitigated by feature engineering. There's also a lot of spatial dependencies, like all the geographic nuances, and there's temporal variability. The times of day can play a difference, which brings us to future work. So to deal with the temporal issues, we could add in more temporal factors and take into account the time-based variable fluctuations in supply and demand to get a more dynamic understanding. The hybrid models would be another approach, which means we could combine the latitude and longitude data with the binary zones, which could potentially lead to more accurate and robust results. And then another option would be adding in more data, just like we did with the baseballs. We could add in more real world data like weather patterns or other events in New York. So overall, our results just underscore that choosing the right data representation to balance accuracy, generalizability, and computational efficiency are all important things to consider. Thank you so much for listening. Bye.
Thank you.